mixed, the mixture will not melt until it has reached that second heat. You know, some parts are not well mixed, still pure paraffin, they might melt, but the integrity of the combustion chamber will not be lost until 90 degrees Celsius. So that was a good reason for adding alpha olefins. And also, as you can see on the graph to your right, these are the rheology results. Now the axes are quite small, but it represents viscosity, so shear rate. And as you can see, the increase in alpha olefin increases viscosity. So this is important to us because as the combustion chamber, as the combustion happens actually, you know, the paraffin will form a liquid, you know, and then vaporize. So the increase in viscosity probably results in an increase in combustion efficiency because the increased drag, you know, it still increases the linear time, as did the swirling injector. So this is something we want. And also this increase in viscosity results in an increase in brittleness when the grains are solid. So what this can do for us is that if the grain is brittle, but not too brittle, some small shards will break off simply because of the combustion, the viscous drag actually. So these small shards will increase the surface area and result in a higher thrust. So this higher thrust is important. Since this hybrid rocket is heavier than most rockets we've launched, we needed a really good thrust to reach the desired thrust-to-weight ratio. So this increase in brittleness achieved that. And also the last parameter, which the additive effect, is the increase in the regression rate. So again, this regression rate directly increases thrust. It's not a linear relation, but you know, more regression rate means more fuel is burning. The fuel is burning faster, and it means effectively a better thrust if we keep the same combustion efficiency.
So now I'm going to talk about the test bench and how we operate the fire test. This is a 3D render of our test bench. We designed it to be as fully modular as it can, so we can test different diameters of combustion chamber and different length. It supports thrust up to 15,000 newtons, and there's a security factor of 2 on that parameters, so we make sure that it is truly safe to test our model. We also have a data acquisition system that we made. We want to make sure that we measure all the combustion parameter. We have a lot of measure that we need to make. So first we have the longitudinal load cell that we need to calculate to measure the thrust. We also have the lateral load cell that will measure lateral thrust that we don't really want. We don't want to do thrust vectoring, but it's important to know if we have that. We also have load cells below the oxidizer tank, so we can have the mass flow rate during the fire test. We have a lot of pressure transducer. We have the pressure in the tank. We also have the pressure before the injection and after the injection, which is basically the combustion pressure. And finally, we have combustion chamber thermocouples, so this makes sure that we have a successful ignition of the engine. During the first 2 or 3 tests that we made, we had a lot of difficulties with our data acquisition system, so we decided to program software in Python, and we're using a LabJack hardware to do it. So this is an example of the interface that we have. We have all the graphics here in lifetime, so we can monitor all the parameters that I showed you before, and we also have the minimum and maximum values on your right corner. So this permits to see what was the max thrust or max pressure that we have. These are actual pictures of the 2.5 years. It is a project that we are working on since 2013, and these are great pictures that are we're really proud of and that we wanted to show you. So this concludes the presentation. We are very confident that since we invested a lot of time, we are very confident that we have all the performance to reach the desired altitude of 10,000 feet. Sorry. And we are very proud to be here this year at the Second America Cup to show you our hybrid rocket. These are the references that we have to support the presentation. And we also want to thank all the stores that we have. We have a lot of sponsors, Switchlog, that give us all the fluid circuit part. We Bombardier, Altium for the hardware software. And we also want to thank Polytechnique Montreal to give us all the support financially, and also the faculty to invest and build our rocket. So thank you. We're now ready to answer your question. Yeah.
Can you tell me about the development of your swirling injector, the shape of the hole, size of the hole pattern?
Sure. So what we have done, we make a smaller version of our hybrid rocket engine. So we are using a 4-grain Cesaroni casing, and we did the first test on the 2-grain Cesaroni casing. So what we done, it was a little bit of at first a shot in the dark. So we knew what the oxidizer to fuel ratio that we want with the length and the mass of the paraffin wax that we have, and using NASA CEA software, and we knew the oxidizer fuel that maximized the thrust. Knowing the oxidizer to fuel ratio, we know the mass flow of oxidizer that we want. So this affects the number of all the injector area that we want. For the swirling injector, the references that I showed you before, all you are around 45 angle of 40 holes, and we decided to make it less inclined.
We added a kind of bevel to it to help vaporize the oxidizer into the aerosol mix that I speak as well.
And so now so was the first shot in the dark, and as after the fire test, we measured the mass flow of our oxidizer, and we were within 1% of error with the No, only parameters that change here is the injector. We have the same mass of fuel, the same geometry, and also the same oxidizer and amount, and also the pressure. So it's really so we did it to see what is the injector influence, and so we give all the other pressure constants.
So you didn't start the plan for that particular vector. You're starting your plan to try and swirl the vector and see what.
Yeah, because since it took 2 years prior to the first test, 2 years of development, we knew that we needed more than traditional engine to reach this thrust. So a way to do that was to create the injector. Research was made, and it was found that the swirling greatly increased performance. So one of the first tests we did was with the swirling injector compared to the traditional injector, and we did all the prior tests with the swirling injector. All the tests after, so with the swirling injector.
So we basically just did the traditional injector ones, and we decided to go with the swirling injector.
Describe your core, is it cylindrical, do you have a progressive or regressive burn?
We have a regressive burn, so it's kind of make a plateau during the permanent regime. So it's kind of flat, the truss is flat and the pressure. But when we start to have a little less fuel and oxidizer, Ross curve is regressive. So,
What's the shape of the core?
Cylindrical. It's a cylindrical core. It's pretty much a square with a whole combustion chamber. You mean the geometry?
Usually cylindrical is progressive because it gives you increased surface areas to the valve.
Yeah, it's that's pretty intuitively. It's logical. We're not sure why in our case it's regressive because we see when we open the valve we have a peak as we expect, but then it's a plateau and it's kind of regressive. So we're not sure why. Maybe it's because of the pressure drop, because the oxidizer. What we think, but it's true. It could and should be progressive, but it's regressive.
Yeah, the oxidizer is fed and is self-pressurized with its own vapor pressure. In the as a feed system, no, there's no cooling. In the motor itself, since we have a quite short, around 7 seconds, it does not tend to get that hot. But we do have our spacers for the pre-injection, pre-combustion and post-combustion chamber are made of a 3D printed PMMA, and this serves for ablative cooling as well as insulation.
Yeah, so we test the motor during the winter, and we know that the temperature very affect the pressure. So what we've done, we have heat blanket. So we always heat the oxidizer tank to have the expected pressure that we will have here. So around 850 PSI.
And also, yeah, to add on that, we thought about it, and we have a bleed valve and a purge valve in case pressure gets too high and it's become dangerous.
Yeah, we have a fully developed ground station. So we have a pressure transducer in the oxidizer tank, and we also have a kind of a warning that's kind of close, and another warning on our computer that says, okay, now we need to purge, so let's do it. So thank you for your attention, and I will. Yeah, I hope to have a great competition. Thank you.
Alrighty then. You guys got the cover? No. Alright, I'll get that next one. In the meantime, I need someone to run the live stream. It's pretty simple. It's just go on YouTube, stop the last one, start the next one. Go on a quick title, and we'll talk about it later. But then, someone will come to you purchase and then you'll pass it off to them.
J'en ai beaucoup que je fais.
You can go make it now. It is